In this video we're going to look at how to prepare an element library for use with spectra that have been measured using a hard X-ray source. In this case we're going to look at spectra that were measured using a gallium liquid metal X-ray gun that is monochromated to have an energy of 9.25 kiloelectron volts. There are two consequences to the photon energy. First of all, the photoionization cross-section and therefore the relative sensitivity factors must be calculated for a given photon energy, in this case 9.25 kiloelectron volts, and this will differ from the standard aluminium or magnesium cross-sections in the default CasaXPS library. Secondly, the range of possible energies that are available to the hard X-rays is far greater than the standard X-ray guns of aluminium and magnesium, so the library will include very many more binding energies compared to what you would see in the standard library. So when we start CasaXPS, the library that is loaded is designed for aluminium and magnesium X-ray sources, so we'll need to load an element library that corresponds to the type of data that we're about to examine. To prepare the element library, we first of all need to load some data that were acquired using this hard X-ray source, and these data have been provided by Ben Spencer at Manchester University, and they arrived as a PXT file, that is the file format that was written by the data system. However, you can convert a PXT file in CasaXPS through the Convert to VAMAS File dialog window that is available either from the File menu or this toolbar button here. And when I select the data file with the extension .pxt and press Open, then data are read from the PXT file, they are entered into a new VAMAS file, and a set of VAMAS blocks are then displayed within CasaXPS. The intention is to develop a CasaXPS library that corresponds to the gallium X-ray source. And what we must first of all do is make sure that these VAMAS blocks are indicating a gallium anode, and that is because the element library will display the photoemission lines and the relative sensitivity factors based on the anode label. So let's select these and then use this toolbar button, that is the X-ray anode, and it gives us information about the data that are displayed in the active tile, and it's indicating that the source label is sync, which is designed for a synchrotron source where the photon energy may vary. But in this case we don't need to vary the photon energy. It's simply a case of specifying that we're going to use a source label of GA, indicating we've got a liquid metal gallium X-ray gun. The photon energy is as specified in the file. We don't want to change that. We don't want to change the magnification, which isn't specified, but the resolution of 500 indicates the pass energy for the survey spectrum, and the pass energy may differ for these different VAMAS blocks, so we don't want to adjust that. So once I've indicated that I just want to change the source label to gallium, I've got all of these selected. If I say OK, now the source label for each of these will be the gallium as indicated on the first VAMAS block. The reason that we changed the source label is because a file was prepared that includes a short form for an element library. That is to say, it contains the element, the transition for the element, a binding energy, a cross-section, and then the source label that was used to calculate the cross-section. And this table was provided by Ben Spencer from Manchester University, and this was done so that on the element library and the input file property page we could select the simple table option and then browse and identify a file that corresponds to the table here, which was a txt file, and then say open, and that specifies that the file has been selected, and so we can say using the simple table load, and then it indicates that the file was loaded OK, in which case we now have an element library that is populated with a set of values that correspond to the photoionization cross-sections and the gallium X-ray source. Loading from the simple table has overwritten the current default. So the element library is now purely based on these gallium source labels here. The simple table did not include line shapes, so these have just been defined as a default, and this may not be appropriate for these data. So you can go and modify the element library and create an element library that is appropriate for these data. So if I open this library here, which has been manipulated within Excel, I've got a line shape which is a void function, and also within this file Auger lines have been added to supplement the photo emission lines that were in the original simple table file. And if I want to load a file that is in CasaXPS format, I first indicate the file, so this indicates the file that I'm about to load, and I get to choose between either loading or merging. If I load, I overwrite the current file. If I merge, I add whatever is in this file to the current list. So I do want to load these data, but I need to make sure that I have the right file format. So the file format is a CasaXPS lib format, not the simple table, and I say load. So now I end up with an element library that if I select one of these lines, then the table scrolls and we can see here's an iodine 2s, and you can also see that the line shape is now the void function based on a Doniuk-Sunjic line shape with an asymmetry parameter of 0. There are a couple of points that are worth mentioning about managing CasaXPS libraries. That first of all, whenever you load, merge or modify any CasaXPS library, then when you close CasaXPS, it will ask whether you want to save the file. And that's really the basis of how these files were created. The directory which contains the data that you are working on is most likely to be the place where the library will be saved. So here you can see these library files have accumulated within the same Manchester directory that the original data files were. If you wanted to have access to that library easily without associating it with a specific data file, you can move the library file to the casaxps.lib directory, and this is in the same directory as where the casaxps.exe file is. So this is a subdirectory that contains a set of library files that you can load or merge at will. Then the other option is, if this is in fact the default library that you would like to use with your data, what you do is you move the file that you've just created to the CasaXPS directory, and then if it's called casaxps.lib, it will automatically be loaded when you start CasaXPS at the start of a session. And if at any point you wish to return to your default library, there's a button here that says load default lib, and this will load the element library that is associated with your current version of CasaXPS. Finally, let's look at how we would use the element library to create regions and components. I've just displayed an iodine 2p, and if I bring up the element library and also the quantification parameters dialog window, and then select the region so that we can see here that we have an iodine 2p 3/2 peak. So this is a single peak within a doublet. The element transition field says iodine 2p, and this is not actually within this element library. So what I need to do is indicate that I have the iodine 2p 3/2, and then I can create when line selected, so that when I click here I will then create a region because the region's property page is topmost. So let's do it. So I create a region, and when I look at the region you can see that the relative sensitivity factor and the name has been pulled from the element library rather than simply default values being entered. I can do the same thing for the components property page. If I want to add a component, because the components property page is topmost, when I say create when line selected, then I select the same line, a component is created which I can then say fit. So we can see here that we have a component that for this given background is a Voigt function and spreads quite considerably beyond what you would expect for a normal integration region. So when making use of a relative sensitivity factor such as this one here that's calculated, one really has to work out whether we should apply it to the photoemission peak as defined by a component, or perhaps by some integration region that is much more limited than the one I've got here. Another example of a background type might be the Shirley background, and another choice of the background limits might be as shown here. And so the relationship between signal that is integrated above a background and signal that might be defined by a Voigt function may not be the same as you might expect, especially if we now try to fit a Voigt function to the data with a Shirley background. You can see that there is a difference, and how we choose the line shape, how we choose the background, and how we choose the relative sensitivity factor are all key components of working out quantification by XPS.